From the University of Arizona Distance Learning Program, this is Optical Sciences 505, Diffraction and Interferometry, with Dr. James Wyant. This broadcast is authorized by the Arizona Board of Regents on behalf of the University of Arizona. Any reproduction or retransmission of this course or use of same for granting of credit without the express written consent of the University of Arizona is strictly prohibited.
Well, I'll say hello to everyone. Since we're taping this 8 days before it's going to be shown, I'm not too sure what to say about basketball. I don't know if we still are, if the season's over for us or not. But did you have a lot of fun this last weekend watching basketball? We went to Saturday, my wife and son and I went out to a sports bar where we had the 4 large screens. We had 3 games on at once, and that was enough to almost make me look basketball. I was getting so confused on who was playing whom and whatever. But anyway, fortunately, we won, so that's what counts. Okay, well, we're talking about Fresnel diffraction. And last class we were talking about circular aperture. And I'm going to start out by saying a little more about the circular aperture Fresnel diffraction problem. And let's first just review what we had from last class. Last class we were looking at a point on axis. Say we have a source here. We had some supposed to be circular aperture here, and we had an observation point over here. And we were, Z1 away from the aperture, and the source was Z1 from the aperture, and the observation point was Z2 away. And for some crazy reason, I had a radius here of C. And so we went through here and calculated the irradiance right on axis here. And we got what I think is a very interesting result, that we got that the irradiance here, I of P, is, write down 4I00 of P times the sine squared of squiggle over 2. And the I00 of P was the irradiance that we would have here if the aperture had an infinite size. And so the irradiance here, as we either vary the size of the aperture or move back and forth here, the irradiance on axis varies from 0 to 4 times what the irradiance would be if the aperture had an infinite size. And remember, this squiggle here was equal to the radius squared, so C squared Z1 plus Z2 over lambda Z1 and Z2. And what we said was here that if we have one Fresnel zone, well, just maybe I should write here, just R1 plus R2 was Z1 plus Z2 plus squiggle lambda over 2. So if we had one Fresnel zone, and so in that case squiggle is equal to 1, then we would have that I of P is 4 I00 of P. And so if there's only one Fresnel zone in this aperture, we get 4 times the irradiance we'd have with an infinite size aperture. If there were 2 Fresnel zones, so squiggle is 2, then what the sine squared of, I think I left something out here. Left a pi there. So it's squiggle pi over 2. If squiggle were equal to 2, so we had 2 Fresnel zones, then we have a sine squared of pi, and so that's 0, so the irradiance would be 0. So if we have an odd number of Fresnel zones here, we get 4I00 of P. If we have an even number, then the Fresnel zones will cancel out, and we're going to get 0 here. And if we think for a second about that, I mean, that sort of makes sense, that we know in going across one Fresnel zone, the phase changes by pi here. OPD changes by lambda over 2. So if we go across one, if we have only one Fresnel zone here, things are fine. If we have two Fresnel zones, then for each point in the second Fresnel zone, we have a corresponding point in the first Fresnel zone that would be out of phase by pi, and so they would cancel out. So we had a little drawing here, which we put on the screen, and I'll repeat that again. And that drawing is the following. So this is showing all the Fresnel zones in the aperture, and at the time being, I've made every other Fresnel zone opaque, but so far we haven't. As far as our problem goes, so far all the Fresnel zones are transparent. And then we said we put some aperture here, and so if we allow an odd number of Fresnel zones going through here, we get a maxima in the irradiance. If we have an even number of Fresnel zones, then they would cancel out and we'd get a 0 in the irradiance. If we were to move sideways here, if we want to look at points not on the axis, that would sort of be like moving the aperture sideways here, and we see the problem certainly becomes much more complicated to calculate what the off-axis irradiance is. But right on axis, it's pretty straightforward. Okay. So what I wanted to do now was to add a little material about how you would calculate this, not just on axis, but we can go off axis. And there's a handout over here on the side, and I have to tell you, I had a terrible problem with this handout. Not on making the handout, but I'm making copies of the handout. The good copying machine at Optical Sciences decided not to work today, and the bad copying machine worked like it always does. And so when I made those copies, I ended up throwing them away. I thought they were so bad. So I went down and used another one. So they're fair copies, not super copies. Anyway, what we're going to say a little bit here about calculating the diffraction pattern of this circular aperture. And I'm going to go back here and try to remind you of Gaskell's course that you took. And remember when in Gaskell's course, when you took the Fourier transform of a rotationally symmetric function, there was something that you could do kind of tricky. And that tricky thing was, what's the word I'm trying to think of? Because I'm showing it right here on the screen too. What, the Hankel transform? Did you have the Hankel transform in Gaskell's class? Do you remember? Yeah, okay, good. Did you like it? Yeah. Well, I love it. So we call it the Hankel transform, or sometimes they call it the Fourier-Bessel transform. Now I know there are at least a couple of you in this class who have not had Fourier optics yet, and well, you'll be able to make it through this class without Fourier optics. You really need to have it if you're going to be in optics. But for those of you who've not had the Hankel transform yet, you can go to Goodman's book, and you look at about page 10, 11, and 12, and he goes through the derivation of the why we would want to use a Hankel transform of 0 order here. But in any case, what we're going to do here, I'm not going to go through the derivation for it. You've either had it in Gaskell's course or you can look at it in Goodman's book. But if we have a Fourier transform of a rotationally symmetric function, then we can easily, well, fairly easily calculate the Fourier transform. So remember just our Fresnel diffraction equation we had here, where we had some phase factors out in front, which we won't worry too much about. And inside we had the Fourier transform of however it is we're illuminating the aperture, e to the I k over lambda z2 squiggle squared plus eta squared. So rotationally symmetric, and as long as we illuminate this with something that's rotationally symmetric, then we could use this to calculate, we can use the Hankel transform of 0 order to calculate the diffraction pattern. And if I might zoom in here just a little bit if we can. And I didn't print this out very large, but all this is, and it's in your handout. So this is just the Bessel function of zero order as Mathematica likes to write it. And in the argument here, I put in a 1.22 instead of a 2 that you might often have here. And I also put in a 2 here because I'm going to normalize this such that if we have 0 Fresnel zones, we get a maximum intensity of 1. And so we can just go through this integral here and calculate the diffraction pattern. The next thing I did, and I don't have this in a handout, although I will put it up on the website if you're interested in it, is I put in, what I'm putting in here, we have a phase factor that goes e to the I, number of Fresnel zones times pi times rho squared. And rho is right now normalized to go from 0 to 1. So this would be in NF zones is number of Fresnel zones that we have in the aperture. And I first will plug in that we have 0, in which case what we're really going to have is Fraunhofer diffraction, which we will get to later, but I'll just show a curve for that now. So this is just using this Fourier-Bessel transform, calculating a profile of the irradiance, and we get our normal Fraunhofer diffraction, which maybe you don't recognize yet, but you soon will. But what's more interesting for us right now is that, and this was in the handout, I put in here the number of Fresnel zones, and we plotted 4 plots here. And all this garbage up here is just to get the different colors and line width and stuff here. So it's just the Hankel transform that we looked at previously. And this would be for 0 Fresnel zones, so that's our Fraunhofer diffraction. The green is for half a Fresnel zone. The blue here is for 1 Fresnel zone. And then if I go to 1.5, I get this, goes way down. If I go to 2 Fresnel zones, this actually goes to 0 right on axis. So before we were just calculating things on axis here. But anyway, using this Hankel transform of 0 order, you can do a pretty good job of calculating the Fresnel diffraction patterns for a circular aperture. The next little picture I have here, again, I didn't give you in the handout because I had such a big fight with the copying machine. I'll put it up on the website, though. This was just going through and keeping the, making the area proportional to the number of Fresnel zones. And so we're really going back here. We're looking on axis, and we were increasing the size of the aperture here. And we got this sinusoidal variation that we had expected, which is a max at 1 Fresnel zone, minimum at 2, max at 3, minimum at 4, and so on. So same behavior that we had predicted by hand without using the computer. Anyway, this Fourier-Bessel transform or Hankel transform of 0 order, whatever it is you want to call it, is very useful for calculating these diffraction patterns when you have rotationally symmetric situations. So once again, maybe all that suffering you went through in Gaskell's class was worth it. Okay, going back, and another little review from last class, and then we'll go on to new materials. Remember the opaque disk? And we went through using Babinet's principle, and we found out that we have source here, observation point here, obstacle right there, and we looked right on axis, and we found that right on axis the irradiance was equal to what the irradiance would be on axis if we took the opaque disk away. And that was true as long as we're far enough away from the opaque disk that all these approximations that we've made do not break down. So this is a kind of a really amazing result that you get this bright spot right on axis. If we increase the size of the disk, Remember we saw that the irradiance right on axis did not change a bit. Okay? If we move off axis slightly, the irradiance will change very fast as we increase the size of the disk. And as the disk becomes larger, the total amount of energy contained in this direct diffraction spot will decrease, but the irradiance right on axis remains fixed. So irradiance on axis, independent of size of disk. Okay. Amazing result. So any questions on that? Okay. Well, then let's go up to starts new material here. And this is section 13.3. And this is going to be called zone plate. Well, I think, so far we've seen that looking at these Fresnel zones is a nice way to get a good feel as to what's happening to the irradiance. And thinking of circular apertures made up of Fresnel zones works out to be very, very convenient. And we found that the irradiance on axis depends upon how many Fresnel zones we have present in the aperture, and for an odd number of Fresnel zones we get a peak. For an even number of Fresnel zones we get 0 right on axis. So maybe, if we think here for a second, maybe that's saying that if we think of every other Fresnel zone is kind of, any two consecutive Fresnel zones are kind of canceling out one another, because Fresnel zones all have the same area. And for any given Fresnel zone, the Fresnel zone next to it has a corresponding point that's out of phase by pi. So the idea is that maybe we can get more light on axis if we cover up every other Fresnel zone. Instead of having a completely transparent aperture, let's cover up every other Fresnel zone and see if we can't increase the amount of light we have, at least on axis. So we're going to use alternate Fresnel zones. Okay. And go back to where we talked about circular apertures before, and we had this little quantity squiggle here. And so let squiggle be a positive integer n. Then we would have, and so going back here, so we had this equation that we had for squiggle, and we're going to let that be an integer n. And we're going to go back and solve for c. Except now I'm going to call it rho, and in fact I'm going to call it rho sub n. So this is the radius of the nth Fresnel zone. And so rho sub n from this expression right here, which also comes from right here. Rho sub n will be equal to lambda z1, z2, supposed to be a 2 times n, divided by z1 plus z2 square root. Okay? So that's the radius of the nth Fresnel zone. So now what we're going to do is we're going to take this thing, and we're going, where we've made every other Fresnel zone opaque, and we're going to add up the irradiance of these, of the light coming from all these open Fresnel zones on axis anyway. I'm only going to look on axis here. And so U of P will be whatever we got from the first Fresnel zone. Second one we don't use, whatever we get from the third, fifth, so on out to nth one. Okay? And so we have to go back and we have to do this integral, adding up all these phases, but it's not, turns out to not be too hard. So we'd have u sub p, and we had this factor in front, u double zero of p, and we had an I out here. And for the first Fresnel zone, when we go back, all we're doing here is that we had, remember from our notes, or the interested student can go back and check it in notes, I guess, e to the I pi q dq from 0 to 1. Before, what we had, we just said from 0 to whatever the value of q became. But now we're going to do, for the first Fresnel zone, this would be the integral. And now from the second one, well, the second one we make opaque, so we don't have to worry about that. So the integral from 0 to 1 goes away. And now we have the integral from 0 to 3. Okay. And then we'll have the integral from, well, 3 to 4 we don't use, so 4 to 5. So on out to n minus 1 to n. So we have to do all these integrals. And fortunately it's simple, so I can still do it. And so what we'll get here is minus u double zero of p. The first guy, we get e to the I pi minus 1. Next integral here, we get e 3I pi minus e to the 2I pi. And I might as well write down the next one too. E to 5I pi minus e to the 4I pi. So on up. Now this becomes pretty nice. All these are 1s or minus 1s. And so what we have here is u double zero of p times n plus 1. That's kind of nice. And so we will get that I of p is I double zero of p times n plus 1 squared. So we have n Fresnel zones. So this agrees with what we had last class, where n was equal to 1. We'd have a 4 I double zero of p. But as we keep adding in Fresnel zones, as long as we block out these guys that are out of phase by pi, the radiance goes up pretty fast. And we end up with, for n Fresnel zones, we end up with n plus 1 squared times what it would be if we had a perfectly clear aperture. And so we get a pretty, I'll say a very intense spot or point. Okay? And so by taking our aperture here, I might as well get rid of this, use the whole thing. Taking our aperture, and we broke it up into Fresnel zones. We made every other Fresnel zone opaque. We end up with a much brighter focus spot. Okay? Now I say a much brighter focus spot. I mean, that's true only if going across each one of these only if each one of these transparent things is a single Fresnel zone. Okay, and so if we were to keep the wavelength constant, if we kept the wavelength constant, if we kept this constant, and let's say we kept the overall size of this constant, if I move along here, I mean, there's only one location in space, at least to the right here, one location in space where these guys are going to have, each transparent portion here is one Fresnel zone. If I move to different locations, I'm going to have a different number of Fresnel zones in each transparent portion here. So, you know, I like to think of the light coming from each open area here as a vector. And so what we had here, for the right location in space, all these vectors added up, or in phase. But if we move to a different location in space here, now these vectors, of course, which represent the light coming from each transparent zone, you know, the vectors are no longer in phase. And so we will have less irradiance. And in fact, we may end up with a situation where all these vectors come right back on themselves and we end up with zero irradiance. And if we think for a second, when would that be? Well, if I changed my location here such that going across any given zone, I had not one Fresnel zone there, but let's say I had two Fresnel zones, then the irradiance on axis would be 0, because the two Fresnel zones are out of phase by pi, and they would cancel out. So as I move along here, you know, someplace I'm going to have a lot of light, where each open portion corresponds to a single Fresnel zone. I come in here half that distance, and now, let me make it a little bit simpler before I say that here. Let's say I illuminate this with a plane wave, then I can say what I want to say here. And these are my Fresnel zones. And when we make every other one opaque, we'll call it a Fresnel zone plate. Okay. So now, if I came out here, just the right location, each one of these is one Fresnel zone, I get a bright spot. If I come in here half the distance, what would we say about each one of these zones now? Let's see, phase goes like rho squared over 2r. So if I come in half the distance, the OPD across each open portion would be, out here it's pi, half the distance, it would be 2 pi. OPD, no, rho squared over 2r, I change r, reduce r by a factor of 2, the OPD doubles. So if I come in here half the distance, across each one of these guys I'd have two Fresnel zones, and so that's going to give me 0 intensity. If I come in here, so this is, say, 1/3 of this distance. Now how many Fresnel zones will each one of these contain? I think maybe you've been watching too much basketball. If you're way out, if you shoot a basket from center court, how many points do you get? Oh, okay, that's right. You have 3 Fresnel zones here. Okay. So that's 1/3 the distance. If I come in here to 1/4 the distance, now I'm going to have 4 Fresnel zones. Not so good. Cancel out. You know, 1/5 the distance, I have 5 Fresnel zones. And 4 of those will cancel out, and I have 1 left. Okay. So what we have is we have something here that acts a lot like a lens. Okay? It has focal points. But it doesn't have just a single focal point. It has one here, and it has one at third the distance, fifth the distance, and so on. And in fact, if I think here for a second, and going from one Fresnel zone to the next Fresnel zone, well, going across a single Fresnel zone anyway, I should say, it's pi. If I go from one open area to the next open area, it's 2 pi difference. And so not only do I have a nice focal point over here, which I'll call F, I can also have light not just coming to a focus here, but I can have light diverging from a point over here, a distance F on the other side. So this zone plate has both positive and negative focal lengths. So let's write down some equations and we'll come back to this. So the equation we had here was that rho sub n squared was lambda z1, z2, n over z1 plus z2. Okay. And we could play with this for a second, and we get 1 over z1 plus 1 over z2 is equal to n lambda over rho sub n squared. My pen is dying. Or, you know, what the way maybe you like to think about this, we had a rho sub n squared over z1 plus a rho sub n squared over z2, and that was n times lambda. I'll put a 2 there, a 2 there, and a 2 there. This was the OPD, illuminating, viewing, and for the nth Fresnel zone, that OPD is n lambda over 2. Okay, so we have this right here. Let n equal 1. 1 over z1 plus 1 over z2 is lambda over rho sub 1 squared. And this has focal properties like a lens, and it has focal properties like a lens where the focal length is. So focal properties like a lens where the focal length is what? Rho sub 1 squared over lambda. So it's the radius of the first Fresnel zone squared divided by the wavelength. Oops. Okay. Now we said that, so if we take this Fresnel zone plate here, maybe illuminate it with a plane wave, we're going to get a focus over here F away, where F was rho sub 1 squared over lambda. And we will also have a negative focus over here, F away. So F is plus or minus rho sub 1 squared over lambda. Okay. So I guess we have a lot of chromatic aberration, don't we? If we change the wavelength, the focal length changes a lot. We go to longer wavelengths, the focus is closer to the Fresnel zone plate. Shorter wavelengths farther away. Now we said if we went in here half the distance, each opening would have 2 Fresnel zones, and so that's not good. Every other one would cancel. You know, one would cancel the other one. If we go in here, so we have a third of the distance, now each opening here would consist of 3 Fresnel zones. 2 of them will cancel, and I'm left with 1. And so we have another focal length here, which would be like rho sub 1 squared over 3 lambda. plus or minus again. If I go in here a quarter of the distance, now each opening would consist of 4 Fresnel zones, and they would cancel one another, so that doesn't give me anything. But if I go in here a fifth the distance, now each one opening would have 5 Fresnel zones, so I have another focal length here of plus or minus rho sub 1 squared over 5. And then so on. So we get all these odd orders. The even orders cancel out. If I go in here to this third order, so each opening had 3 Fresnel zones. 2 of them will cancel, so I'm left with 1. So the amplitude would be 1/3 here, what I have there, or the intensity here would be 1/9 what I have for the primary focus. Okay.
Instead of rho 1?
No. This should still be rho 1 here. I mean, what we're saying is that you understand how we got to here for the focal length. So the lens, the zone plate has this focal length. But we're noting that if we move in to a third that distance, and so that would be rho sub 1 squared over 3 lambda, then we will have 3 Fresnel zones in each opening. 2 of them will cancel, and I'm left with 1, so I'll get another bright spot. But it's 1/3 of this distance. And so it's 1/3 where I have a rho sub 1 here, not a rho sub 3. Question or? Yeah, okay. So this would be 1/9 their radiance on axis of this, and this would be, what, 1/25 of that, and so on. And we have positive and negatives. Okay. Any questions? So this little thing, I mean, it actually works very well. If we made a little transparency of this, we could set this up in a lab, and as you move along axis, you do indeed see the foci. Have any of you played with zone plates in lab? No? Okay. Jeez, I need to get a lab going with this course, because it's fun to play with. What if I take this and I make a picture of it, and I get a negative? So what if I have a negative of this? How's that going to change the focal properties? Any wild guesses?
Switching to the even.
No. If I make a negative of this, so the center is negative and this is positive. This is transparent. I still would have half a wave for the primary focal point. I'd have half a wave OPD going across here. And then opaque, and then half a wave again. And so the focal properties actually remain the same. But there's one difference in the light that's brought to focus. What difference might that be? So I'm going from one of these guys to the next guy. There's a pi. And so when I make the negative of this, the amplitude of the light transmitted through that will differ by pi. And so if I used a negative for this Fresnel zone plate, I would get the same focus spot, but it would be out of phase by pi from what I get from this. So maybe I should write that down. So make negative of Fresnel zone plate. So at primary focus, OPD across each transparent zone equal lambda over 2. Therefore, same focal properties. But Fresnel zones are, say, phase of Fresnel zones changes by pi, because we're using different Fresnel zones. And so the amplitude of the light, the intensity is the same, but the amplitude has to be changed by pi. Okay. Well, let's see, what else can we say about this plate? Well, we got a lot more light by covering up the Fresnel zones that differed in phase from the adjacent Fresnel zone by pi. So we cut out every other one of these. Let's say that I make this completely transparent, but I put on some coating here that covers up every other Fresnel zone and changes the phase of the light going through that Fresnel zone by pi. Okay? So all of the Fresnel zones are going to be transparent now. Every other one has a coating on it that changes the phase of the light going through it by pi. What can you say about this Fresnel zone plate now? Not much. Okay. So remember, we got rid of every other Fresnel zone because it was pi out of phase with the adjacent guy. But now we keep that Fresnel zone, but we put a coating on it, adding pi to it. So now all of these Fresnel zones are going to be in phase. And so how much more light will we get at the focus? Twice as much amplitude, 4 times as much intensity. Okay. So a phase Fresnel zone plate produces 4 times the radiance. Okay, that's kind of neat. Well, let's see, what else can we say here? Well, another thing. So let's put our plate in here. I'm going to illuminate it by collimated light, but you don't have to illuminate it by collimated light. It's going to focus like a lens anyway, but it's maybe easier to see with collimated light here. So we have our Fresnel zone plate here. We're illuminating this with collimated light. So we have one beam going to focus here. And we have higher orders too, but I'm going to not worry about them. And we have this other beam that appears to be coming back from here. So this is F. And this is F here. And these two beams are overlapping. I mean, when this comes to focus, that's not so bad, pretty intense, but we do have this other beam in the background here. And the focus of this is going to be right along this axis, so if I were to take my zone plate, it's right along some axis here coming out. Now, let's say instead of using, a centered zone plate, let's go off axis and use a portion like this. Okay? So now what we're doing is that I'm not using the whole zone plate, but I'm going to use only, I'll block off this portion here. I'm going to use only this portion up here. So now we have this light coming to focus. And we have this light here coming out here. So now the beams are separating in space. So we don't have the overlap of the beams, which is kind of nice. And this is a lot like a hologram. In fact, later in the course we'll talk about holograms. And one way of thinking of how holograms work is you think of them in terms of zone plates, and you like the orders to separate, so you think of them in terms of off-axis zone plates. So we've picked an off-axis portion of this zone plate. Okay. Well, the concept of Fresnel zones and zone plates, it's very powerful in helping you solve problems. And so I'm hoping that you feel that you are experts on Fresnel zone plates. Or if not, you will be by next week or so. Any questions before we go on? How do you make a zone plate? Well, this one I made by writing a computer program and drawing it out. But a common way of making a zone plate, other than using a computer, is the following. I mean, we look at this thing, and it looks a lot like interference fringes. Of course, now, I mean, I'm hoping that at this stage in the course, everything you see looks like interference fringes, okay? But if I took a beam, interfered a plane wave with a spherical wave, and recorded that on film here, and if I process this film properly, I could produce something that looked just like this. Now, what if I, by processing the film properly, what I meant was I really get this 50% duty cycle. So this is opaque for one zone, and the next guy is transparent for the whole zone, and then opaque, and so on. Let's say I go through my photographic process, and I have these fringes, but instead of having binary pattern like this, let's say I had a sinusoidal pattern. So the amplitude transmission went sinusoidal. How do you think that would change the properties of my Fresnel zone plate, the imaging properties of the Fresnel zone plate? If I had a perfectly sinusoidal amplitude transmission of the zone plate. It might image better, it might not have all these orders. And in fact, if it were perfect sinusoidal, you'd have a +1 order and a -1 order, and none of the higher orders. And as I change, so if I made this on a piece of film, and I changed the nonlinearity of the development process, what I would do would be to simply change the amount of light in the different orders. And if I got this sinusoidal distribution, I'd have only plus or minus first order. If I got this binary thing where every other zone was opaque, then I'd have only the odd orders. If I got something in between, I might also get some even orders. But anyway, the most common way of making something that looks like a zone plate is to use interferometry and simply interfere two beams, getting the fringes. Or if you have a computer and plotter, you can, or printer, you can draw out your Fresnel zones and make them this way if you want. Any other questions on Fresnel zone plates? Okay. So we've been talking about Fresnel diffraction for circular apertures, and we found that thinking about Fresnel zones was very nice. We also said that this zero-order Hankel function was very nice for calculating the diffraction pattern, since the Fourier transform of a rotationally symmetric distribution turns out to be the zero-order Hankel function. But what I want to do now is to go to something that's not rotationally symmetric, and this is to go to a rectangular aperture. And so this is section 13.4. What we're going to look at is Fresnel diffraction for a rectangular aperture. And this is still Fresnel diffraction. Okay. So the situation that we're going to do is the following here. I have a little diagram I'll let you copy. I did not make a Xerox of this for you, but we start off here. I mean, it's the same diagram you've seen many times in this course. Source is over here someplace in the x prime, y prime coordinate system. We're going to put some aperture over here, which is going to be a rectangular aperture in the eta squiggle coordinate system, a distance z1 away. And then we're going to come over here a distance z2 and look at the diffraction pattern here. So the first thing we have to do is to go through and calculate these distances here. And so we'll come back to the drawing. This gets a little messy. It's covered in a million different books. So in the observation plane, we're looking for u of x and y. And an old formula here, that's going to be the integral of h. We'll write down what h is in a second, but it's going to be a function of x and y and squiggle and eta. And u, however it is we illuminate the aperture, and then we have to integrate over the aperture. And since now we're talking about Fresnel diffraction, we'll write here that u is a over r prime, just a spherical wave, e to the I k r prime times whatever the aperture function is, p. Later p is going to become a rectangle. So that's our equation that we have to solve. And I guess r prime, we can write down what r prime is here if we want to. And so, and we're going to make the normal approximations that we've been making. And so this u is whatever p is, our aperture function, times a over z1. So we're going to approximate down here r prime is z1. And then we go through our normal expansion up here. Get e to the I k z1. And then, as before, we get e to the I k over 2z1 times squiggle minus x prime squared. Never have enough space. Plus eta minus y prime squared. Finish our bracket. So now we need to take this mess and plug it back up into our expression here. And let's see, what did I not do? I didn't write down h, did I? I wrote down what u was, but I didn't write down h, so I guess I better write down h before we plug everything in there. So h of x, y, squiggle, and eta is what? 1 over I lambda. We have e to the I k z2 over z2. And we have an e to the I k over 2 z2 x minus squiggle squared plus y minus eta squared. So they're normal Fresnel approximations. So we have u, we have h, and so now we're going to plug that into this mess and get another mess, bigger mess. But I need to take a sip of coffee before I do that. So how much do you think we're going to beat Maryland by? By the time the people watch this tape, they're going to know. Any wild guesses here? Is there anyone here who thinks we might lose to Maryland? No one. Don't have the basketball fans here. Boy, I don't know. Well, okay, here. So let's plug this in. See what we get. We get u of x and y. Probably all the basketball fans have gone over to watch the basketball games. Maybe. I don't know. So we're going to get an a over I lambda z1 z2 e to the ik z1 plus z2, and then we get a mess here. Minus infinity to infinity, whatever the aperture function is, oops, squiggle and eta. And then we have an e to the I k over 2z2 x minus squiggle squared plus y minus eta squared. Okay, you can read that. X minus squiggle squared plus y minus eta quantity squared. And then coming down here, e to the I k over 2 z1 squiggle minus x prime squared plus eta minus y prime squared. D squiggle, d eta. I think my second pen is wearing out. Okay. That's a mess. I think we'd have to agree with that. So what can we possibly do to have less of a mess? So this is what we were trying to do here. We had a source here, we have some aperture there, and we're trying to look at the diffraction pattern over here. Well, the common thing that we do at this point is the following. We're going to look only at one point here and have the source here on axis. And so what we commonly do at this point is the following. We say let x prime equal y prime equal x equal y equal 0. So we've moved a source to the origin here, moved an observation point to the origin here. So the drawing we would have, I'll just give you a second to draw this in. The drawing is that we have, here's the aperture that we're dealing with, and we're now saying it's a rectangular aperture of width A and height B. We have put the source on axis here, and we put the observation point on axis here. And so this is going to simplify our equations a lot by making the x prime, y prime equal to 0 and the xy equal to 0. But it doesn't quite give us what we want. I mean, I don't care so much about moving my source here, but I really want to find the irradiance distribution in this whole plane. I don't want to be limited to just a point at the origin. So what we normally do is that we keep these points fixed here. And to calculate the irradiance here at different points, what we're going to do is we're going to move this aperture around. Okay? So we're going to keep the observation screen fixed, and we're going to cause the diffraction pattern to move across this point by simply moving the aperture around. So maybe I should write that down, and then we'll work with that and see what we can do. So we will fix P, so the observation point is fixed, and we're going to cause the pattern, diffraction pattern, to sweep over it by translating the aperture. In its own plane. Now, is that equivalent? And the answer is almost, but not quite, probably. As we move this around here, the pattern on the screen is going to change a little bit in size, and distribution of the radiance will change a little bit just because we're moving this around. But it will turn out to be very good approximation as long as Z1 is much larger than any motion of the aperture. So this is good approximation. If aperture motion is small compared to Z1. And I think if you go to Goodman's book, he avoids this problem entirely by making Z1 infinite, and saying we're illuminating the aperture with a plane wave. But I don't want to restrict ourselves to that. I'm just going to say that Z1 is large compared to how far we move the aperture. Now, it turns out there are three cases then that we can study here, three interesting cases anyway that we can study using this approach. There are three cases to be studied. The first case will be A and B, small compared to Z1. And then the entire, Z1 make that. And if that's true, the entire pattern can be examined. Okay, I'll come back to the drawing in a second. Show you what A and B are. Okay, so we're saying that A and B are small compared to Z1, then we can look at the entire pattern. So what are A and B is the question. So remember, A and B were the dimensions of our aperture here. A is the width, B is the height. So what we're saying is that as long as the dimensions of the aperture here are small compared to the distance to the source, then moving this around is fine, and we can sweep out the entire diffraction pattern here and determine what we have here simply by looking at this point, point P, moving this aperture around, and we'll calculate the irradiance at that point as we move the aperture around, and from that infer what the irradiance is across this plane. Okay, is that clear? So that's one case that we can study, and that will be the first case that we'll study. But let's write down the other two cases, because we'll do them today too, well, after we take a break here. Next case will be A is small, B large. So we're saying that the width is small, height might be. Now we're saying that the pattern can be investigated as the aperture is translated parallel to the squiggle axis. So let's say that. I'll write that down, then we'll come back to the drawing. So pattern can be investigated as aperture translated parallel to the squiggle axis. So back to the drawing. A is small, this can be large, and we're still okay getting the distribution here by translating this parallel to the squiggle axis. That'll work okay. That was the small dimension here. Okay, so that works. The last one, it's almost amazing this last one works, but it turns out to work very well. We're going to have both A and B large. Now is that the pattern can be investigated near the geometrical shadow. Okay, and this is a case, turns out to be a very interesting case, of a semi-infinite screen with a straight edge, or like a knife edge. So case of semi-infinite screen with knife edge. Okay, and it's amazing this works, but later we'll show that it does work. And so this would be, instead of having just a rectangular aperture here, we're going to put in a knife edge. So essentially half is opaque and half is transparent. And as long as we stay near the geometrical image of the knife edge, things work out well. And that will, well, we'll go through that calculation later. It's pretty neat. And it's contained in a lot of books. Essentially any book on diffraction would have that case in it. Okay, so is everyone with me now? What we're doing? We're going to go on axis here. We're going to keep this point fixed, and instead of wandering around here finding the irradiance, we'll keep that point fixed, and we're going to move this aperture around here and cause the irradiance to move across that point. Okay? Well, I'll get started on this just a little bit, and then our time will be up for this taping. And for those of you sitting here, we'll start up again in half an hour. For those of you watching this on TV, we'll start up again in 2 days, I guess. So we're going back to this horrible equation we had here. And we're going to plug in x prime is equal to y prime equal to x equal y equals 0. And we're going to end up with another horrible equation, actually. But there will be hope here. So now we're looking for the amplitude at point P. And that's going to be equal to, just from our previous horrible equation, A over I lambda Z1 Z2 e to the ik Z1 plus Z2. Horrible thing here. Integral of e to the I pi over lambda squiggle squared plus eta squared 1 over Z1 plus 1 over Z2 and d squiggle d eta, and who knows what the limits are. Eta 1 to no, we're going to take care of the pupil function right now. The limits here will be eta 1 to eta 2 and squiggle 1 to squiggle 2. So I don't know just what these are, but when I plug in that the size of the aperture is A and B, width A, height B, some way we're going to calculate what these limits are. And so that would take care of the pupil function. And so as we go through this, remember what we're doing. We're keeping, the size of this aperture is fixed, but we're going to move this aperture around here. And that's why these limits are like they are. And, well, this mess out in front here. A over I lambda, Z1, Z2, e to the ik, Z1 plus Z2. I'm going to call that C prime. Okay. I won't call it C because I'm going to have a C later, but right now I'll call that C prime. So I think what I'll do at this point, we have a couple minutes left, but I think this is the point to break here. And what we will do next class is we will come back here in some way play around with this to get it in a form that we can solve for the diffraction pattern. And so let's take a break now. And for those of you sitting here in class today, we'll come back at 12:45 after you've had lunch or whatever, and we'll start up and finish this problem, and then also go on to some other interesting things in Fresnel diffraction, and then we'll start Fraunhofer diffraction. So those of you watching this on TV, we'll be back in 2 days. Otherwise, those of you in the classroom will be back in 30 minutes. Thank you.